Thank you, Mary. And I have to say thank you to White October for really taking care of us. As a speaker, I've never felt as well taken care of as in the Lead Dev conference. Right. So the question I'm going to try and answer is, what on earth does it mean to build AI software? But before we dive into trying to answer the question, let's talk a bit about whether this is even a worthwhile question to ask. So I'm sure you've seen articles like this. AI is more important than fire or electricity. Every company must become an AI company. AI is going to do amazing things with autonomous cars. AI is going to help us cure cancer. And my current personal favorite, post-Brexit, we're going to ensure that the UK is the best place in the world to develop artificial intelligence and the technologies of the future, but artificial intelligence gets special mention. Question mark, question mark, question mark, better paid jobs. So it's clearly an AI spring. Everyone is really excited. Everyone is talking about it. Everyone wants to do it. And I think it's also a bubble, right? And the bubble will pop, and winter is coming. And if you think this is a Game of Thrones reference, it's not. It's a pure AI reference. There's something inherent to the field where you're promising intelligence, you're promising learning, that means you're over-promising and you never quite reach there. So AI has gone through lots of winters, and you're never quite sure when they're going to come, and you're never quite sure how long they're going to last. Now, the question is, if winter is coming, why should we be asking ourselves, is AI a worthwhile activity, and why should we worry about how we build AI software? Well, I think we've actually reached a tipping point. After 60 years or so of concentrated research, even though VCs, press, and politicians may move on, the tools and techniques we have now are here to stay. And we've seen in the talk before on AI with JavaScript great examples of how easy it is to use these tools and the level of maturity that there is. So I think because of the easy access to the tools and because of the level of maturity and the fact that they actually solve problems, even though we're in kind of a hype bubble right now, it's still really important to worry about AI and how do we build software with AI. And then there is kind of a bigger picture thing, and this might, not everyone might agree with it, but I think as humanity, we have huge problems to solve. Climate change, feeding everyone, educating everyone, keeping everyone healthy. And technology is going to play a huge role within that, and software is going to play a huge role within technology. And the next step for software needs to be along the lines of what AI techniques are saying, because we need that scalability, and we need to deal with this level of complexity. So according to me, at least, it's a worthwhile question. But how can we have a discussion about AI, about engineering with AI, that is not hand-wavy and we're talking about concrete concepts, clarity? And let me give you examples of discussions that are hand-wavy. And this is my favorite one. CEO reads an article in Forbes about forward-thinking CEOs. They're all doing AI. So they walk up to their CTO and says, we need to add AI to our products as well. OK, how do you think AI is relevant to us? AI will help us scale output, improve how we do things, and do new things. I've read all about this in that Greenfield Labs white paper. That white paper does exist, and it does say that. And I wrote it. And it's not false. Well, we were told before, make things a bit more exciting. So it's not false, but it's hand-wavy. So any builder, any maker of things is going to see through that and say, well, hold on, even though I'm not an AI expert, doesn't all technology help us scale, improve, and do new stuff? Well, yeah, I guess you could say that. But AI learns, and it's intelligent, and it improves itself. What does learn mean? What is intelligence? How do we specify these things? And typically, at this level, the discussion becomes a bit circular now. So the CEO goes back to, well, I read an article, and it says, forward-thinking CEOs do this. And you kind of give up. So the next discussion you could have is go to your team and say, any ideas about how to use AI? And there's two extremes this might play out. One is just, we don't want to know. A more likely one is we have all sorts of ideas. Let's use Tensorflow. Let's use Spacey and do natural language processing. Let's buy some NVIDIA GPUs. I heard that's a thing. Let's build chatbots. Right? And again, how can we have a discussion about engineering with AI that is not hand-wavy and refers to concrete concepts? So let's try and answer this. And we're going to do it by looking at what is AI, try and give a definition that's useful to this discussion. And then we're going to talk about how do we describe and build systems where decision-making is delegated to machines. And in that second bullet point, there's a huge spoiler about where the first bullet point is going to get us. But let's take the steps. So what is AI? I find it really useful to look at this 1955 research grant proposal written by McCarthy, Shannon, Minsky. And they say, we propose that a 2-month, 10-person study of artificial intelligence be carried out during the summer of '56 at Dartmouth College. The study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. An attempt will be made to find how to make machines use language, form abstractions and concepts, solve the kinds of problems now was 1955, reserved for humans and improve themselves. And if you think this is a tall order, they then go on to say, we think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a whole summer. There's the seeds of the first AI spring and winter in these 2 paragraphs. But leaving that aside, what does this tell us about what is AI? Well, to me, it says it's a field of science. It attempts to understand how intelligence works, and in order to validate its hypothesis, it builds machines that simulate models of intelligence, right? We're trying to figure out how intelligence works. Fine, that's really interesting. Question is, when in a company you're building products, someone says, we want AI, well, what does that mean? You want the science of AI? Why aren't people going around saying, we want math, we want physics? They're great sciences. So I think we just need to accept that concepts have been confused a bit, and we need to do some translation. Right, so when people say they want AI, what we need to translate it as is we want virtual assistants that help people solve support issues. We want to automate processes. We want better prediction. We want machines that can act autonomously in changing environments, and so on. And what is common between all these different things? The way I like to think about it is we want to delegate decision-making to machines. So there's something that we're doing over here that involves humans and humans taking decisions, and we want to give it to the machines over here. Right? Now, there might be any number of ways to achieve that. It just so happens that AI provides lots of really interesting techniques to achieve this delegation of decision-making to machines. But the problem we're trying to solve is this. It's not AI in general. right? OK, so this reframes the question as, how do we delegate decision-making to machines? And then, to me, the question becomes, how do we describe and build systems where decision-making is delegated to machines? Why is this useful? I think we talk a lot about what different types of AI can do, but it's important we start building shared terminology, right? So that we can describe systems in terms that everyone understands and allow patterns to emerge, because that's really significant in order to progress the practice of building AI software. Also, I think it's really useful to be able to distinguish between the what is it that we're trying to build, what sort of decision-making is taking place, before we start worrying about, well, how are we going to solve this decision-making problem, right? Because there's lots of techniques, and it's that usual thing. If the only thing you have is a hammer, everything is a nail, right? So we need to be able to distinguish these two things. So let's try and do this now. In order to talk about the what, I'm going to pull some ideas from a subfield of artificial intelligence called agent-based engineering. And agent-based engineering essentially said, look, we've been building intelligent systems for a long time. It's about time we started learning what are the commonalities, how can we describe them, kind of exactly the question we posed to ourselves just a minute ago, right? And within agent-based engineering, we're going to draw ideas from a framework, conceptual framework called SMART, that gives us a way of thinking of the world that focuses on the what and doesn't worry about the how. And the model itself is quite formal and so on. We're going to do a very light and digestible trip through it. So SMART starts with the environment. Here's an environment, and it's described by attributes. Fine. Within this environment, you have entities. Entities is anything that can be described by a set of attributes. Again, nothing particularly interesting. And then it goes on to say, well, some of these entities, so some of these things in the environment, have capabilities. Right? What are capabilities? Capabilities are sets of discrete actions that can change the attributes of the environment. Again, kind of similar things, sounds like object-oriented programming and so on. It then goes on to say, we have agents. And agents are objects, so are things with attributes and capabilities, but they also have goals. So what is a goal in precise, concrete terms? Well, it's a desirable state of affairs in the environment. So I'm an agent, Ronald. I have a position on the stage. My goal is to finish this presentation and not have tomatoes thrown at me. I have capabilities like speaking, transfer knowledge, and moving backwards and forwards on the slides, right? So this gives us a way to start grounding the what, and then we can start thinking of different types of agents, and this is where it becomes a bit more interesting. But because describing things like this becomes boring quickly, we're going to talk about the story of my new startup, You. You builds rain protection devices. It allows you to live in a moisture-free world, and obviously, we use AI. So we got some seed funding, and we built U1. Now, the way U1 works is that when it rains, you pick it up, and you hold it on top of your head, and you open it, and it stops the rain from hitting your head. Right? So in the world of SMART, this is what we call a passive agent. It doesn't actually have any goals itself. We, the users of this other object, ascribe a goal to it. It's the agent through which we achieve our goal, but itself doesn't have any representation of this within it. Now, if you think of it, most software are passive agents. They have no desirable state of affairs they want to reach. What they're doing is allowing us to manipulate their capabilities, to affect change in the environment to achieve our own goals, right? So not particularly interesting, but our marketing is good. We got some more funding, and we built U2. Now, U2 is an active agent. So things flip now in that the goal is explicitly defined within U2 itself. So it has the goal of keeping its user moisture-free. And it can do that any number of ways. In this case, there is a rain sensor and an actuator that opens the rain protection device and a drone that follows us around so we don't get wet. Now, at this point, I started getting excited. I actually thought, well, maybe there is a startup in this. And there is. It exists. Like, Google it. Someone has built this. OK, so U2 is an active agent, and that's really exciting. I got excited. But you can take it further, and you can say, well, you can also build proactive agents. So the way U2 works is it would wait for rain to come, and then it pops into action, right? So it's reactive. A proactive agent can also say, well, I'm not just going to wait for rain to arrive. I'm going to monitor weather patterns and suggest paths that are going to ensure that we never get in that undesirable state of the environment, right? So we're going to proactively manipulate the environment to get to a point where we're achieving our goals, right? And the way we describe this is we say, well, this device has more self-direction. It has more ways of solving the same problem, the same goal. Now, if you think of it, how much software right now can solve the same goal in more than one ways? It's really not a lot. We kind of went from passive agents, most of software, to proactive agents. A very small amount of software does this right now. And at this point, U is reaching unicorn level, and you can go ahead and build an autonomous agent, right? So you're taking it one level up, and you're saying, instead of explicitly assigning a goal and kind of delimiting the space of the scope of functionality within that single goal, we're going to use a higher order abstraction, which we call motivations. The simplest way of thinking of motivations is like utility functions. And motivations lead to the generation of goals, right? So you can have motivations like reduce contact with moisture, minimize energy usage, don't disturb passerbys, and based on those motivations and how they play out, you generate goals which are desirable state of affair in the environment, right? So you might decide, I'm actually going to close this rain protection device because I might disturb a passerby. So you have this scale, kind of, which goes from the passive agents, we ascribe goals to them, to reactive agents, proactive agents, autonomous agents. And as we were describing all these things and the goals they're trying to achieve, everything was grounded in very specific concepts. So to me, this is really important because it brings clarity. We can talk about what we're building without kind of using just generic, it's intelligent, or something like that. And we didn't talk about how we're going to solve the problem, right? This is just the what. So let's talk about the how. And there is one really key point I want to make here, and it's, I guess at the biggest level, is to get you to think about the entire range of AI and not what is particularly popular right now. And that's the distinction between data-driven and model-driven AI. And I'll explain what I mean by this. So we said what we're trying to do is delegate decision-making to machines. Now, in order for machines to be able to achieve that, they need a model of the world. They need to know when I activate capability X in order to affect change Y in the environment, what does that mean? What are the consequences of that, right? So we need something to base our decisions on. How do we derive this model? There's two extremes. On the one hand, you can design the model. You can explicitly design the model. And my favorite designed model is Newtonian physics. Right? Newton didn't say, OK, we have to figure out how this apple is going to bounce off the ground, so let's go to an orchard and drop 100,000 apples and measure that and collect all this data and then pass it through a neural network, and we'll get to some prediction of how apples are going to bounce, right? What Newton did is said there's some fundamental laws that govern the relationship between force, mass, acceleration, and we can use these laws in order to predict what's going to happen in the environment, right? And huge swathes of AI are all about explicit model representation, reasoning, analyzing possible states, right? And you have things like traffic control, train scheduling, all sorts of applications with that. And that's extremely efficient because you can do a lot of checking around it. On the other hand, there's all sorts of problems, like the very important problem of, is there a cat in this picture, that actually we tried, but we can't write a set of explicit rules that will give us a reliable answer, right? So in that case, we need to discover the model. So if you cannot have an explicit set of rules, then you say, OK, well, let's use data and use huge amounts of data. This is from kind of what was the seminal moment for machine learning in 2012 when Hinton started talking about convolutional neural networks, right? And it's 60 million parameters, 650,000 neurons, which actually these days is not even that big. So you can use data in order to discover patterns and predict what's going to happen. What we need to be careful as we're building software is let's not try and discover things that we've already figured out. So let's not do let's drop 100,000 apples and measure it. You can. And impressively, I just found this out 2 days ago. Someone did it, or a group of people did it. They said, well, can we rediscover physical laws through neural networks? And yes, you can. You can feed it the data, and it comes up with a reasonable level of accuracy, I think 97% or something. But is this a useful thing to do? Well, as an academic exercise, yes. Otherwise, I'm not quite sure. So it's useful to discover the model in order to when we have data and we can learn patterns and we cannot do an explicit representation of that model, and there's all sorts of applications for this. And again, the talk before gave us some great examples. Now, whether you're discovering the model or designing the model, I just want to quickly mention, make sure you validate your model. So this is an example from some research that was done with the question, can we recognize criminals from a photo of their face? Now, leaving aside the 10,000 alarm bells that should be raised when you even ask that question, how did they do this? How did they validate, how did they build this machine learning model? Well, they took pictures of people that were arrested, and the assumption there is if you were arrested by the police, you're a criminal. And then they took pictures of people that were not arrested by the police, and the assumption there is you're not a criminal. Now, what did they find out? did they find out the difference between the facial features of a criminal and not a criminal? Or did they just train a model to recognize when someone is slightly ticked off because they've just been arrested by the police and they're having their mugshot taken, and people that are not ticked off because they're sitting at home or in the office and doing whatever they want to do, right? So if you are trying to discover a model, make sure you question what sort of data you're using, what assumptions are you making around that data. Right. The other thing to keep in mind is actual applications are hybrids. Google Maps is a great example of this. Google Maps gives you a model of the road network, which is an explicit representation of the world, right? And then it uses machine learning models, or anyway, some sort of prediction in order to say what the traffic condition is and how to identify the more efficient route and so on. Now, I know what some of you are thinking. Is Google Maps an AI application? It doesn't matter. Let's all agree here. Let's get started today. Let's stop asking the question, is it real AI? Because it's an impossible question to answer unless this was a philosophy conference and we were having some sort of debate around the nature of intelligence. It doesn't matter. The question you need to answer is, did you successfully delegate decision-making to software? Do you have a model of how your world works that is reliable? Go to bed. You've done it. It's OK. So, as a summary, going back to our original question, what on earth does it mean to build AI software? The way it helps me think about it is that it's really about how can we delegate decision-making to machines. And in order to delegate decision-making to machines, we make use of a number of different techniques, a lot of them coming from artificial intelligence, but they can come from other fields as well, such as physics. And they can be data-driven, or they can be model-driven, or a hybrid. And we need to think about which one are we choosing and why. So we apply techniques to enable capabilities. These are ways to understand the world or to change the world in support of applications. And applications, we can think of them in terms of these agents that are attempting to achieve goals, desirable states of affairs in the environment, and they can be doing it very simply, with very little self-direction, increasing degrees of self-direction, or they can even be autonomous, where they're generating their own goals. That's it. Thank you. I'm going to... Thank you.